Bismillahirrahmanirrahim. Hello everyone, how are you? Why your friends didn't attend to this session? What about your other classes? Other classes held in this week or not? I think this week is the last week of your educational calendar. Okay. In your curriculum, this week is the 16th week of our education calendar. Okay. Okay. So probably your classes, other classes, was not held this week. Okay, no problem. We have some complementary subjects, some advanced subjects to give a hint to you in order to do your research in future in this area. So let me go to the slides. In this session, I think one of you can represent his or her presentation. I talk about new subjects about 1 hour. Let me to share my screen and go to the slides. Okay. Let me to take a record. This session. Okay. As you know, in your exam, in the first question of your midterm exam, I have set a question in that I asked you to talk about how generators use excuse me, let me go ahead. How generators use coverage criteria and test requirements to generate test cases. And in previous lecture, I told you we have an unsolved problem exactly this problem is the first question of your exam. I make this question especially to force you to think about how we can use this coverage criteria and test requirements to generate test cases automatically in practice. And if you remember, we have a slide that we saw this slide in chapter 2 about how to find values to run the function, run the problem according to these test passes. Okay, as you know from chapter 2, from chapter 7, in chapter 7 we again discussed about graph-based coverage criteria such as edge coverage, such as edge pair coverage, and etc. In that chapter we talk about how to cover test requirements by test passes, and we talk about we should provide proper input values to execute each test pass. For example, in this question, as you know, this is a control flow graph for this method. All of you know this method, which determine the index of an element n from an array, a pass array. We have a pass of elements, we have an array of elements, and we want to find one specific element from that array. To do this, this is the same as the sequential search or linear search function. All of you know it. And this is a control flow graph. According to our coverage criteria, we compute some test requirements according to edge pair, according to edge coverage, and as I told before, to covering these test requirements, we should generate test cases to execute this function according to these passes. Okay, but the main problem at this situation is that how we can find proper input or inputs for this function to execute exactly these test passes. For example, when we want to go from node 1 to node 2 to node 5, as you know, we should make a test case. In that we have a pass, we have an empty pass, we have an empty array, because in the first execution of our for loop, we should saw that I is not less than the pass size. This is happen just when the pass size be 0, because the index I started by 0, and when at initial execution of this for loop we saw that the pass size is 0, so this condition could not be satisfied, and we skip simply from this for loop and go to this return statement. So by having an empty array and each arbitrary n, we can pass this execution path 1, 2, and then go to 5. Okay, how we can find these input values? Or in another test passes, you know, we should go to the loop once. We want to execute the loop once. 1, 1, 2, 3, 2, 5. 1, 2, 3, 2, and 5. How we can make an input values to force the program, to force the function, so that execute this execution path, so that we have this execution path. How we can provide this input values? Or for the last test path, we should execute the loop twice. 1, 2, 3, 2, 3, 4. We should execute this loop twice and then go the loop and go to the final state 4. How we can, the main question in this situation is that how we can provide a proper test case so that we have this execution path. We can go through this execution path. How far we can find values? This is the main problem, and this problem remained unsolved till now. This is the main concept of automatic test generation. In this test generation, we mean that we want to generate test data automatically. We want to use all coverage criteria we have learned, we have taught till now, such as input space partitioning, such as graph-based coverage criteria, such as control flow coverage criteria, such as data flow coverage criteria, or logic-based coverage criteria, and syntax-based coverage criteria, as we don't teach them. How we can use these coverage criteria to generate test data automatically? In general, we have three approaches to generate test data automatically. First approach is a random approach. We can randomly check several combinations of our input values or input parameters as our test cases, and we can check by a recognizer to see what of them, how many of them is proper for our testing practice, our testing activity. Which of them can cover some uncovered test requirement. We use it, or we use them. Okay. So the first approach is a random approach. The second one is a search-based approach. I don't know you are familiar with meta-heuristic algorithms. If you had really meta-heuristic, if you have meta-heuristic algorithms such as genetic algorithm, PSO algorithm, ant colony, artificial bees. Are you familiar with these algorithms? Please tell me. Are you studied any of these meta-heuristic algorithms? Are you familiar with these meta-heuristic algorithms? Genetic, PSO, ant colony, and so on. You are not familiar with them? I have a suggestion for you. If you have any other course for next semester, you can take a course titled with evolutionary algorithm to learn how meta-heuristic algorithms could be applicable in different subjects in computer science or software engineering. They are essential for any of you to do your thesis. There are broad areas, there are broad subjects that you can take them as your thesis title, which you can solve them by these meta-heuristic algorithms. One of them is software testing. You can use broadly those meta-heuristic algorithms in software testing, and this is an active area in software testing research communities. Okay, so I suggest you to have a course in this with this title. So the second approach is using search-based techniques, search-based algorithms to find proper test cases for our programs. And the third approach is an approach named symbolic execution. A symbolic execution based approach. In this approach, we use some tools, some mathematical tools named constraint solvers. For example, in this approach, we use some mathematical equations to make some constraints about any execution path, and to have to hold these constraints true, we should find some values for our variables in our program to good execution, to can execute the program in a proper path. So let me tell you about some of these approaches. The first one, as you know, is a random testing, and this is a approach to generate our input data. There are some famous research in literature that uses random testing or directed random testing to generate test values, and this approach have some advantages and some disadvantages. The main advantages of this random testing is the simplicity of this test, scalability of this testing, because we use values in our input domain randomly, and there is no computation, no notable computation to have any costs in any computation cost for me, and so this could be an execute an scalable approach and efficient in computation cost, because we have no computation cost. But there is some we have symbolic execution, because we have no time to talk about these approaches with more detail. I just introduce some videos to see if you want. If you want, you can see these symbolic testing videos to know how we can generate our test data by this testing approach. And you can see these 4 or 3 directed automated random testing. We have 3 videos in this collection, as I informed you before, to know about how random testing can be done in practice, and how research communities, research institutes can use this approach in generating test data. This is the two first approaches. But about the third approach, the search-based approach, I have not seen any video about the search-based techniques. So you can search about the search-based techniques in YouTube and other places to know about them. All of theses today in several universities is defined around these approaches. So these approaches is advanced topics in software testing. I just talk very short about these approaches. For example, in symbolic execution, suppose we have a simple piece of code such as this. In this piece of code, we have 3 variables in this code: x, y, and z. And all of these statements is about computation of some of these based on some of these input values. As you know, in the first statement, we compute the value of a variable a by summation of x and y, and then in the next statement we compare z with a. If z is bigger than a, we run this statement, else otherwise we run this statement. If this condition satisfied, we set the value of b to x minus y, and otherwise we set b to 2 times y. Suppose we want to test this code. As you know, in this code, if we draw a control flow graph, we will have 2 execution paths. In this statement, we should define a branch statement. If this condition be satisfied, we go through the first branch, and otherwise we should go down through the next branch. So in this simple case, we have 2 statements, one for if statement and one for else statement. These 2 statements make our 2 execution passes, 2 different execution passes. So we should define 2 test cases to test these 2 execution passes. And note that we want to know how symbolic execution can guide the finding our input data. In a symbolic execution, we set our input parameters by symbolic values, not concrete values. When we set, for example, x to be, for example, 5, we set x by a concrete value. But when we set x by some value such as s1, we assigned x with a symbolic value. In symbolic execution, we can use symbolic values to define our input parameters, and based on this symbolic value, we go ahead through the execution of our statements. For example, if xb is 1, yb is 2, zb is 3, we can compute a by these symbolic values. So a could be computed as x is s1, y is s2. So the summation of x and y be the summation of s1 and s2. And when z be greater than a, when this condition be satisfied, we will execute this statement. So we set the variable b by s1 minus s2 instead of x minus y. So when this statement could be executed, we can decide according to this condition. So we make, in symbolic execution, we make an equation which is named by path constraint. We can define a path constraint. Any constraint is an equation such as this to define, to tell us when we can execute this execution path. For each execution path, we can define a set of constraints. We name them a path constraint. A path constraint defines the conditions that should be held to execute a specific path. For example, when we want to execute this path, we should have a path constraint according to this equation. In this equation, Z, we know that Z is S3. So, according to this condition, we should have S3 bigger than A. And we know A is S1 plus S2. Okay, so to execute this statement, to have this execution path, we should have S3 value so that be bigger than S1 plus S2. So this is a path constraint. Similar to this execution path, we can define another path constraint for the other execution path. For this path, we should have Z be not be greater than A, but be less than or equal to A. So we define S3 be less than or equal to S1 plus S2. If this constraint be satisfied, we should execute this statement. So for any execution path, we can define some constraints. We know them as path constraints. So to have this first execution path, it's enough to have a value for S3 which be bigger than S1 plus S2. For example, we can have 5 for S3 and 1 and 2 for S1 and S2. As you know, 5 is greater than 1 plus 2. So if we have a test case when we have 1 for X, 2 for Y, and 5 for Z, this path constraint could be satisfied, and this execution path, the if statement, could be executed, can be executed. Okay. And otherwise, on the other hand, when we have S3 and S3 which is less than or equal is 1 plus S2. For example, when we have 3 for S3 and 2 for S1 and for example 4 for S2, this constraint can be satisfied, and we have the other execution path in practice. How to solve these constraint passes in practice? In practice, we don't have to solve any constraints. We just use some automated tools named constraint solver, which are generated by mathematical scientists. Already we have some constraint tools. You can search about them and download some of them and use to solve some constraints. So to solve these constraints, we can use constraint solvers. It's enough to determine a constraint passes for each execution pass. And this is straightforward because this is simple task. Our constraints is defined by our conditions, our branch statements. Okay, for each branch we can make simply a constraint. There is no problem to do this. So one approach to generate test data in practice is using symbolic execution approach. In symbolic execution approach, for each pass, for each execution pass, we make simply some constraint. In this case is 1. This is 1. Some constraint passes, some constraints, and we give them to constraint solver to solve these constraints. The constraint solver, by solving these constraints, by analyzing these constraints, introduce some concrete values for these symbolic variables, so that these constraints be solved. Okay. But in practice, there are some situations that using this symbolic execution could be more complex. For example, in calling some other functions and go down through other functions. Also, we can handle this situation simply, because when a function call is happening in our problem, we can go through that function and define constraints in that function and consider them in main function, and this is not so complex. But when we have not some of these the source code of some of these functions, we encounter with we face with a complex situation. When we have not the source code of some functions, when we use a system calls such as API calls, when we use external libraries such as external DLLs, dynamic link library, in our program, we have no any knowledge about that function, how that function compute its return value. So we cannot use symbolic execution simply. This is a trouble, this is a problem in using symbolic execution. Let me skip some of these complex or advanced feature of symbolic execution and left them for yourself. If you want to work in this area in your thesis, you can use other materials such as videos I have introduced you, or some up-to-date papers about using symbolic execution. One approach to solve the using of symbolic execution when we face to API call or DLL calls is using a concolic approach. Concolic approach is an approach that composed of symbolic and concrete. Concrete means real value. Real values. We use concrete values for our inputs when we have a system call, and we call the APIs or system calls by concrete values, and then we have a concrete result for those parts of our code. So we use both symbolic when we have a source code of our functions and concrete values when we use API calls or system calls. Okay, this approach is named by Concolic Testing, and we want to escape from advanced features of Concolic Testing because we have no enough time. And the last, okay, in the last approach, we use search-based testing. As you know, we have a field in software engineering named search-based software engineering. A search-based software testing is a branch of search-based software engineering in which we use some search-based methods, as I told you, some meta-heuristic algorithms to generate test data in software testing. In this approach, for example, when we want to use a genetic algorithm or we use a PSO algorithm, we start with a random input, then we develop a fitness function to compute how this input, these random inputs are good, to evaluate to what level these input values are good. Okay, then we can execute the meta-heuristic operations such as crossover, such as mutation for some iterations according to our meta-heuristic algorithm, and update the solution to new values, and trace the fitness function to have a better inputs, and finally the best solution is selected by the search based algorithm or meta-heuristic algorithm. So we can use genetic algorithm, PSO algorithm, ant-colony algorithm in finding our test values, and this area is an active area in research. You can define some thesis, you can define your thesis in this area and do some valuable research about generating test cases. Some of your papers, your research paper studies are defined based on this approach. Let me to finish this slides at this point, and I am ready to see your representation. Who want to represent his or her? Miss Naime, as I think, yes, Miss Naime, you can present your presentation. Before she start to represent her work, you can ask your questions about these approaches. Let me stop sharing and enable your user. I make you as presenter. You can share your screen and start your presentation if there is no any question about this subject. Because we are in the last week of our curriculum, I decided to inform these subjects shortly, and so that you have enough time to prepare for your exams. And anyone who wants to know more about these approaches can refer to introduced video materials. Okay, Miss Naime, can you hear me? I think I pronounced your name wrong. Go ahead, please. You are presenter. You can start. You can share your screen. You can turn on your mic. I enabled your mic. I don't have your sound. Please write in the chat box. I enabled your mic. I make you as presenter. Can you hear me? Go ahead, please. You can share your screen. You are not shared. Let me. Please stop sharing. Please stop sharing. In the center of your screen, you have. You can see a button labeled by screen sharing. Your mic should be turned on. Your mic icon is located at the top of your screen. Beside this